This program is brought to you by Stanford University. Please visit us at stanford.edu.
The basic kinematics, the kinematics of the Hubble Law, kinematics of the expanding universe, made one assumption which is motivated mostly by observation, that the universe is spatially flat. Spatially flat means that space at a given instant of time is just ordinary Euclidean three-dimensional space. But the space-time itself is not ordinary Euclidean, I shouldn't say Euclidean, is not ordinary Minkowski space. Minkowski space, let's just compare the two. Minkowski space, just to remind you, is the space of special relativity, space-time of special relativity, and it has a metric or a proper time element that's given by the sum of four terms, or the difference of four terms, dt squared minus dx squared. And I'm going to put this in a bracket, minus dx squared plus dy squared plus dz squared. Now, this is the term in the bracket is a dead giveaway, of course, that space is flat. It's just good old Cartesian, ordinary Euclidean space, where the size of a line element, dx, dy, dz, is just given by Pythagoras' formula, three-dimensional Pythagoras' formula. The new element in cosmology, and now when I say the new element in cosmology, first of all, I should say the new element in the general theory of relativity is that the coefficients here, which are simply in this case 1, minus 1, minus 1, minus 1, first of all, there are more of them. There can be things like dx, dy, and dy, dt, and so forth. But the coefficients can depend on position in space-time. That means that the coefficients are fields. And basically, they are the generalization of Newton's gravity. Well, Newton didn't think in terms of fields, but we can think in terms of fields. They're the generalization of the Newtonian fields of gravity, the coefficient functions which go there. Now, observationally, cosmology appears, the universe that we can see through telescopes, appears to be, on the whole, I'll call it featureless. Of course, it has features. The features are galaxies, planets, stars, clusters, superclusters. But that's all small potatoes. That's all small stuff. On the scale of billions of light years, certainly on the scale of billions of light years, on the scale of several hundred million light years, the universe is very featureless. Just the same everywhere. Homogeneous is the word. Homogeneous, it's isotropic. It means it looks the same in every direction on such large scales. And this is somewhat of a slightly larger surprise to cosmologists. Incidentally, the isotropy and the homogeneity has been with us since the very beginning of cosmology. Very beginning of cosmology, meaning post-Hubble cosmology. From 1930s or 40s or whenever cosmology, modern cosmology started, it was always assumed that space was homogeneous. Not space-time, but space is homogeneous and isotropic. And that was given a name. It was called the cosmological principle. And once it's a principle, it has to be right. And so therefore, it's not only a principle, but we proved it. We proved it by calling it a principle. Of course, it of course has never been mathematically proved or never argued from any basic theoretical underlying principle. There is none. But remarkably, the more that we look out into space, the more we see that the principle looks to be very, very accurate on the large enough scales. So isotropy and homogeneity, and one additional fact, space looks flat. Space looks flat, which means that we were not so far off by writing dx squared plus dy squared plus dz squared, but while it looks flat, it also is expanding. So the picture you should have roughly in the back of your head is a flat sheet of rubber, and the flat sheet of rubber is being stretched at a certain rate. But it's infinite, it's flat. Now, of course, we don't know the universe is really infinite. How well do we know that the universe is either infinite or flat? If it's perfectly flat, of course, it's got to be infinite if it goes on and on forever. If it's perfectly flat, unless there's some sort of walls out there, and nobody thinks there's walls out there, it will go on and on forever and ever. So a flat universe is also likely to be an infinite universe. But of course, we don't really know that the universe is either infinite or perfectly flat. We know it to the same degree that if we go out in the backyard or out in the football field and survey the geometry of the football field, we could drive stakes into the football field, stretch strings between the stakes. By stretching the strings between the stakes as tightly as possible, we construct straight lines. We can put several stakes in and create triangles and measure the angles of the triangles. And what we find, of course, to a very high precision, is that triangles behave just like triangles in flat space, namely the sum of the angles adds up to 180 degrees. What do we learn from that? We learned that if the Earth is curved, the curvature is small, which is another way of saying that if the Earth is a finite sphere, it's a big sphere, much, much bigger than the field. When I use the word field now, I'm not talking about gravitational field. I'm talking about the field that we surveyed. It's precisely the same in cosmology. Astronomers do a kind of cosmic surveying, measuring triangles, a thing in the sky over there, a thing in the sky over there. That gives you an angle. You may have some reason to believe that you know the distances involved, both to the objects and also between the objects. Assuming you do have some good reason to believe those things, you are measuring the properties of triangles. And remarkably, those triangles, of course I'm simplifying the story a little bit. What you really measure is a little bit less direct than that, but that will be, it effectively comes to that. We measure triangles, and we find the triangles behave like Euclidean flat triangles in ordinary Euclidean space. Okay. So apparently, to a high precision, space itself is flat, but it's expanding. To make it expanding, all we have to do is put into this equation, it's dt squared, just good old time, minus a scale factor, a of t squared. It's squared because everything in the equation is squared. The units, as always, we'll take the speed of light to be equal to 1. And in that case, the units of time and the units of space are the same. The units in this equation are the squares of lengths. And so if we take a to be a length, namely the distance between two particular points as the points separate and go apart, then we should also think of the x's as not having any dimensions. There's two ways to think about it. You can either think that a has no dimensions and the x's have dimensions of length. The more conventional way to think about it is the x's here have no dimensions. They're simply labels of points. And when you say that the that the distance between 2 points, or the separation between 2 points, is delta x equals, let's say, 5, that's not a statement about how far apart they are. That's just a statement of, well, here's the way to think about it. Again, think about the expanding rubber sheet. We draw coordinates in the expanding rubber sheet, and those coordinates stretch and expand out with the expansion, so that going from x equals, let's put it over here, 0 to x equals 1 over here corresponds to different actual physical separations at different times. At an early time, the actual physical separation in meters between 0 and 1 might be some tiny, tiny distance. Late in the universe, after the universe has expanded many, many times, the distance between 0 and 1 may be very large. That distance is characterized by a of t. So the actual distance between points, if delta x were 5, would be a times delta x, or 5a. And a is a thing which, since it varies with time, it must have some dynamics. There must be some equations governing it. There must be some equations governing how a of t expands with time. So that's our goal this morning. That's our goal this evening, is to work out some of the equations governing A. Now, I should tell you right now, the general theory of relativity allows curved space. When I say space, I don't mean space-time, I mean space. It allows space to be curved, and as long as it's homogeneous, which means the same everywhere, there are 3 kinds of spaces which are homogeneous, any one of which could be the right thing to write down here. As I said, observationally, we're in luck. It looks like space is flat, so we don't have to write anything very complicated. The other 2 possibilities are that space is round, like the surface of the Earth. It's a sphere, but of course it's not a 2-dimensional sphere. It's a 3-dimensional sphere. A sphere, ordinary sphere. Incidentally, let's get something about terminology. When one talks about the Earth, the whole Earth, the body of the Earth, the bulk of the Earth, the rocks in the inside, the mathematical term is a ball. A ball means the solid Earth. The term sphere refers to the boundary, refers to the surface of the Earth. So a sphere is a 2-dimensional surface. Okay? Let's just talk about a little bit what a sphere means. First, a circle. The circle you can just think of as the locus of points x squared plus y squared equals some kind of radius squared. If r is 1, then it's a unit circle. So the locus of points which satisfy x squared plus y squared equals r squared is just a circle. And a circle is a 1-dimensional space. And mathematicians would call it a 1-sphere. A 1-sphere because it's 1-dimensional. What would you call the interior? Two-ball. Two-ball. Or a disk. All right? The special case of 2 dimensions, it has a special name of its own. It's called a disk. But if we wanted to use the generalized mathematical terminology, we would call it a ball, a 2-dimensional ball. But the boundary of the ball is, of course, a circle, and it's a 1-sphere. All right, so if we add a z squared to this, then we get a 2-sphere, the surface of the Earth, or something like that. And it's pretty easy to visualize. I can see the surface of a sphere in my head. I cannot seem to free myself of the 3rd dimension. I cannot seem to see that sphere without also seeing what's outside the sphere and what's inside the sphere. But I know that mathematically, the surface of the sphere, without regard to what's inside or outside, is a mathematical space that can stand by its own and does not have to be embedded in 3 dimensions. The reason we have such a damn hard time seeing 2-dimensional spheres without the inside and the outside is evolutionary. We have been built and constructed to recognize 3-dimensional space, and we have not been built and constructed to be able to see directly 2-dimensional space without it being embedded in the 3rd dimension. But then we come to something even worse. This is a 2-sphere now. This is, the surface is a 2-sphere, and the interior is a 3-dimensional space, the ball, or the 3-dimensional ball. But then it gets worse. We can add another coordinate here. Now, I can't even draw it for you. I can't draw it for you, but I can tell you that, what is this? This is the locus of all points whose 4-dimensional distance from the origin is fixed at r squared. If I could draw it, I would, but I can't because I have to be able to picture 4 dimensions just in order to be able to see the 3-dimensional sphere. This is a 3-dimensional sphere, just as when I just had 3 coordinates, I was thinking about the 3 directions in which you would embed the 2-dimensional sphere. The 2-dimensional sphere is 1 lower dimension than the number of coordinates. If I add another coordinate, then I construct a 3-sphere, the interior of which is a 4-dimensional ball. But forget the interior, forget the exterior. One possible kind of geometry that we could live in is the 3-dimensional sphere, the 3-sphere. Now, you can see from the 2-sphere that every point on the 2-sphere is the same as every other point. Of course, the real Earth, the North Pole, is different than the equator, but just as a geometry, as a geometric construction, a sphere is really quite homogeneous. Every point is like every other point. And so homogeneity does not force space to be flat. It allows, for example, a sphere. Moreover, if you are at a point on the sphere and you look in different directions, everything looks the same. And so a sphere is not only homogeneous, it's isotropic. A person on the sphere. And we could invent a cosmology. In fact, it was always the most popular cosmology until experiment sort of said, well, maybe it's not right, which was to replace the flat plane here by the sphere. I won't write down the metric of a sphere. It's not important, but just think about the sphere as a space, and if I multiply it by a of t, then as a grows or shrinks, it corresponds to a shrinking or expanding sphere. Okay? It does not make sense to ask, well, if we think about the Big Bang as a time when the sphere was very small. Now remember, we're not talking about a 2-dimensional sphere, we're talking about a 3-dimensional sphere. But nevertheless, the best I can do in terms of drawing is to draw a 2-dimensional sphere. If we start with it very, very small, then all the particles that were in it are squeezed together, obviously. They're in no sense at a special place on the sphere. It's not that all the particles were in some place and got shot out of that place out into space. They were on the sphere. The sphere was very small. And so the particles, whatever they were, whether they're galaxies or electrons, they were all very, very close together, squished into some very small space. How small? We don't know how far we can trace things back, but we can probably trace things back to the point where the observed universe was no bigger than a cranberry or something. So we can trace it back a long ways, and that's as far as we can go. Okay? with observation. So we start with a space which might be as big as a cranberry, filled with some large number of particles, and then started expanding. The particles spread out. Okay. The further apart they are, the faster apart they move, because there are more little segments in between. So further apart, in fact, if they weren't moving relative to each other faster, they couldn't have gotten further apart. So the further apart they are, the faster they move. That's closed, finite, spherical universe that was originally the most popular. And our universe may be like this. It's conceivable that it is like that. But if it is, the sphere is so big that, like the Earth, we can't see its curvature by small-scale surveying. And when I say small scale, 10 billion light years is apparently a small scale because we don't see any curvature. So we might as well then replace the sphere by the flat plane, the three-dimensional plane, which is three-dimensional space. But the picture is the same. We have, well, roughly the same. We have a plane with a lot of particles in it. If you like, you can think of it as part of a gigantic sphere. But it's being stretched apart. It's being spread apart. And as it spreads apart, the points which are embedded in it are also spreading apart from each other. And they're spreading apart at a rate which is proportional to the distance between them. That's the Hubble law. Now, we can take this space and we can draw coordinates on it. The coordinates move as the space expands. When I say they move, what I mean to say is that as the space expands, the coordinate separations between neighboring points expand with it. Coordinates like that, which expand with the expanding space, are called co-moving. Co-moving coordinates are coordinates embedded in space which expand with it. In those coordinates, every galaxy is at a fixed place. It's at a fixed place because that's, of course, an approximation. That's an approximation. It's an idealization. But on a big enough scale, it's pretty much true. If it's not true of individual galaxies, it is true of superclusters. And as the universe expands, the location in the coordinate mesh here of any given galaxy stays fixed, but the separation between them increases because of the scale factor. Okay? So if you like, the scale factor, when you rule these coordinates, and you call this x equals 0 and x equals 1, then the scale factor is just the physical distance between x equals 0 and x equals 1. This distance between x equals 1 and x equals 2 is twice as big. And so that's, we can write that as distance between points is equal to a times, let's call it delta x. Now, I showed you the last time, but I want to go through it again because it is important. The Hubble law, deriving the Hubble law. This is the physical distance between 2 points. And this delta x could be measured along any axis, of course, but if I happen to measure it along the x-axis, let's do it along the x-axis. This is delta x here. And just for simplicity, let's keep along the x-axis. The galaxies don't move in the coordinates x. That means if I time differentiate, if I take 2 galaxies, and delta x is now the separation between the 2 galaxies, delta x does not change with time. Supposing I want to time differentiate this. If I time differentiate it, the left-hand side becomes the velocity between the 2 galaxies. So on the left, that's the time derivative of the distance. On the left, we have the velocity. On the right, we have the time derivative of the scale factor. Again, time derivative being represented by a dot, times delta x. That's the velocity. Now let me divide that and multiply it by a. Why did I do that? Because I wanted to get rid of delta x by itself and replace it by something more physically measurable, like a real distance. So I multiplied and divided by a in order that delta x here could be replaced by d. And what do I get? I get that the velocity is a dot over a times the distance between points. Now, a dot over a may depend on time. The scale factor depends on time, so does its time derivative, but it doesn't depend on where you are. So this equation, which tells us velocity in terms of distance and in terms of a quantity which doesn't depend on where you are, is Hubble's law. Velocity is equal to Hubble constant, which isn't really a constant, times distance. But now we know what the meaning of the Hubble constant is. The Hubble constant is the ratio a dot over a. So what we measure when we measure the Hubble constant, when we look out, measure the velocity of galaxies, divide it by the distance to a galaxy, we always get the same number, incidentally. If we look out at galaxies in that direction at 100 light years, or no, we have to look out, sorry, 100 million light years. We look at some galaxy out there. We compute a Hubble constant by dividing its velocity by its distance. We look out at another one in that direction, which is 600 million light years away. We divide the velocity by the distance. We get the same Hubble constant. So,
excuse me.
Yeah.
Looking at two different places, I'm looking at two different times.
Yeah. Yes, you're entirely right. We have to worry about that. But only if we look at exceedingly large distances. And the reason is the Hubble constant itself, a dot over a, varies on a time scale of roughly the age of the universe. All right? So that means if we're looking out to distances which are small by comparison with the age of the universe, otherwise we have to take it into account. To take it into account, to take the variation into account, we have to know how it varies, how a and a dot varies. For that reason, we have to have, well, not only for that reason, but for many reasons, we would like to know the equations which determine how a varies with time. Okay? So that's what we're going to work out tonight. Oh, there was one more geometry, one more mathematical, yeah.
Does the scale factor affect the propagation that we perceive light or gravity at a great distance between the two galaxies?
All right. So let's ask, what are the rules for light propagation? The rules for light propagation is that along a light ray, d tau is equal to 0. Let's just remember why. Let's just draw good old special relativity again. This is a light cone, the trajectory of a light ray, and along that trajectory, dx is equal to dt. That's why it's at 45 degrees. Of course, only when the speed of light is set equal to 1. Again, always the speed of light is 1. Along here, dx is equal to minus dt. But along both branches, dt squared is equal to dx squared, or dt squared minus dx squared is equal to 0. It's another way of saying that the proper time along a light ray is always 0. one way of thinking about a light ray is that it's a trajectory of zero proper time. That rule extends into the general theory of relativity. D tau is equal to 0. So let's see what it says. Imagine a light ray moving along x. Y and z are not changing. It's just moving along x. We can forget y and z. What it says is that dt is equal to a of t times dx. What I've done is just written, I wanted to make this whole thing 0. So dy and dz are equal to 0 by assumption, light ray going along the x-axis. And that means dt squared must equal a squared dx squared. For motion along the positive axis, that would just say dt is equal to a of t times dx. Now, we could work out a kind of velocity of light. Not the ordinary velocity of light, but we could ask how large a distance delta x. Now, delta x is not a true distance, remember. It's just a label. Okay? But we could ask, this light ray, what is the amount of delta x or dx in a given time dt? And that's easy. We just divide by dt. And we find that dx by dt is not a constant, but it's 1 over a of t. So in these coordinates, light seems to slow down as the universe expands. It's not really slowing down. It's just that a given dx corresponds to a bigger and bigger distance as time goes on. So in order for light to have a uniform velocity, since dx gets to be, well, since distance, true physical distance, for a given dx grows with a, this is just a statement that the true, ordinary, conventional velocity of light is uniform. But if expressed in terms of dx and dt, the light ray seems to slow down.
Would it be equivalent then? An equivalent statement would be, to Hubble's law, would be that light gets slower the further you look away from us. Light goes slower the further. It's either that or the universe is expanding or equivalent.
You could probably find a way to twist it into the statement that light appears to go slower and slower as you move further and further away. But you'd have to do all kinds of funny things to lengths, and it's probably not the best way to think about it. But I'm sure you could.
Is there any evidence from the spectral lines from the long distance that at the small levels light is going at a regular speed of light?
Yeah. Well, what do you mean by the regular speed of light? How could they be? What would an irregular speed of light mean? It would mean that light isn't going as fast as light?
Well, we know that on the whole, the spectra from the galaxies is redshifted.
Yeah.
Is there any microscopic evidence from the individual atoms in the galaxies that it isn't redshifted?
There's a lot of evidence that the dimensionless constants of nature are the same everywhere.
And always have been. And always have been.
Say it again.
It always have been. It didn't change.
Yeah, it always has been. Okay. What would you mean by the dimensionless speed of light? Let's try to think of some physical unit of time. My Timex watch is not the one I want to use. The time that it takes to an electron in the inner orbit, in the first excited orbit, to go around the hydrogen atom. Okay, that's a good unit of time. Let that be my unit of time. Okay, how about a unit of space? Oh, well, a unit of space could be the size of an atom. Okay. I could ask, how long does it take for light, or how many revolutions of the electron does it take in order for light to cross the atom? Okay. that appears to be the same everywhere in the universe. Okay? The time that it would take light to travel across an atom where time is measured in some physical unit. We don't have to use, we could use some mixed units. For example, instead of using the orbit of an electron, we could use some vibrational frequency of a nucleus. Take some particular nucleus and look at some particular vibrational frequency, and the time for one oscillation, we could use that as a unit of time. And then we could ask, how long does it take in that unit of time for light to cross an atom? Okay. That is some relationship between scales in nuclei and scales in atoms, and it's a non-trivial fact that that seems to be the same every place in the universe. Now, of course, the argument is indirect, but that seems to be a good assumption. That's what it means to say that the light travels with the same speed everywhere. It's hard to imagine what it would mean for light to not travel with the speed of light. But
when the universe was the size of a cranberry, light actually would have been able to traverse across that very rapidly.
Right. We'll take one light cranberry. No, one. That's not quite right. It's upside down. But it could be a unit of time called a light cranberry. Okay. All right, that's the basic setup. Now, as I said, I didn't say, there is one other mathematical geometry that has the property that it's the same everywhere. Okay? In 2 dimensions, it's the negatively curved. The sphere is a positively curved geometry. What does it mean to say it's positively curved? It's a statement about triangles. If you take a triangle on a sphere, it's pretty apparent that the angles sort of bow out, and so the sum of the angles on a sphere is always greater than 180 degrees. In fact, you can make a triangle with three 90-degree sides to it, 3 90-degree angles very easily. So the sum of the angles is always greater than 0. That's called a positively curved space. And it's true both in the 2-dimensional sphere and the 3-dimensional sphere, the 4-dimensional sphere. If you make triangles, the sums of the angles are greater than 0. All right, are greater than 180 degrees, and that's called positive curvature. There is also the negatively curved geometry, and it's harder to draw. It's a saddle surface. I'm not going to work out its mathematical properties today, but it can be. It stands on its own terms as a geometry without having to embed it in space. But if I embed it in space so that you can see it, it would look like a saddle surface. It may not look to you like every point is the same as every other point, but the mathematics of the saddle surface is such that it has uniform curvature everywhere and it's negatively curved. The meaning of that is if you draw triangles in it, the triangles are sort of pinched in, and they have a sum of angles less than 180 degrees. This is also uniform, isotropic, homogeneous, and any of these 3 geometries is a candidate for an isotropic homogeneous cosmology. As I said, experimentally or observationally, at least on the scales that we're familiar with, it looks flat. Okay, now let's come to the equations governing the expansion of the universe. We started it last time, but let's get back to it. Let's call this point over here us. That's us. And let's draw a sphere around us. It's a big sphere so that it contains many, many, many galaxies and clusters and superclusters and so forth. And let's look at some galaxy over here. It's moving away from us. We know that. Let's write down, well, first of all, first fact. And this is a fact really if space is flat. Even if it's not flat, it's close to being a fact. It's a fact of Newtonian gravitational theory. It follows from Newton's gravitational law and from Newton's equations. It's a miracle. It's what made it possible for Newton to compute things about gravity, is that if you have a sphere like this, and if everything is distributed spherically symmetrically, in other words, if everything is isotropic relative to the point us, there's as much mass here as here as here as here as here, so that everything has nice spherical symmetry, then it's a theorem about the inverse square law, that the force on a particle over here, the assumption now is that we're working with coordinates in which we are at rest. We will just arbitrarily use a coordinate system, a frame of reference, where we are at rest, and velocities mean relative to us. Accelerations mean relative to us. Velocities, accelerations, motion now means relative to us. Then it's a fact of Newtonian physics that the net force on this point here only comes from things inside the sphere, and things outside the sphere, the forces just cancel. This is maybe well known to you in electrostatics, that if you have a hollow region and some charge distribution on the outside, as long as it's spherically symmetric, then there's no force on any particle on the inside of that sphere. It's only the charges on the interior within which exert forces, net force on a particle. So all of the force on that particle comes from masses in the interior here. Okay? That's one statement. The next statement is that the gravitational force of a spherically symmetric distribution of matter is very simple. A very spherically symmetric distribution of matter on the inside is very simple, and it's just to take the total matter on the inside and think of it as being concentrated as at a point. So the motion of this galaxy relative to us is exactly the same as if all of the mass, as if you ignore all the mass on the outside of the shell and take all the mass on the inside of the shell and place it right at that point. Now, that makes it very easy to compute, or at least to see what's going on with this particle over here. It behaves exactly as a particle in a gravitational field where all of the mass is at the center and concentrated at the center. This is the key thing that made it possible for Newton to do a lot of things with gravity. And it's a thing which allows us to compute the properties of cosmology. Okay, let's put us at x equals 0. And let's call this point just x. I'm going to keep it on the x-axis, but of course it doesn't have to be on the x-axis. First of all, let's write down some equations. What is the distance out to that point? Let's call it r. Now, r stands for radius, but it actually means physical distance, let's say measured in meters, to the point x. Well, the answer is it's x times the Hubble constant. No, x times the scale factor. Not the Hubble constant. X times the scale factor. Remember, the relationship between actual physical distances and scale factor is that you multiply the coordinate distance by the scale factor to get the actual physical distance. So the actual distance to this object over here, r, is equal to x times the scale factor, and it's the scale factor which changes with time. Particle moves because the scale factor moves away from us because the scale factor changes with time. What is its velocity? The velocity of the thing moving away from us is x times a dot. Now, let's remember now that we can pretend. We can pretend that this is an equivalent problem of a projectile moving away from us under the influence of gravitating mass point at the center. What is the energy of that point moving away? What would the energy be if all the mass were concentrated at the center and we could ignore all the mass on the outside? Well, there are two terms in the energy, potential and kinetic. The potential energy, let's call the mass of this particle over here little m. The mass of everything inside the shell we'll worry about in a little while. In fact, we'll call it big M. Big M is the mass of everything inside the shell. Little m is the mass of the distant galaxy that we're following. All right, what's the energy of that distant galaxy? It's its kinetic energy, 1/2 mv squared, plus the gravitational potential energy. So the one new thing you have to know is the potential energy of an object in a gravitational field. Anybody not know it? Some people have seen
G over R or something. G over R or something.
G m1 m2 over r. Right? Product of the masses. Right. So then there's potential energy. What's the sign? Negative. Negative because it's an attraction. So when the particle when it gets pulled closer and closer and closer, of course it gets more energetic, but the energy goes down, not up, because things tend to be pulled in direction of decreasing energy. So there's another term, and the other term is minus Newton's constant. The product of the masses, now which masses? The mass of the projectile and the mass that's concentrated at the center in our imaginary simplification. That's all the mass inside the sphere divided by r. That's the energy. And here's what I know. I know that that energy is constant. It doesn't vary with time. That's what I know, that it doesn't vary with time. It could be positive. There's a positive kinetic energy. It could be negative. If gm over r is bigger than mv squared, 1/2 mv squared, then the energy is negative. Whatever it is, though, it is not allowed to change with time. Constant. That would be the property of a projectile moving away from us. All right. I'm going to study the one special case which corresponds to zero energy over here. Later on, I'll come back and tell you what the connection between the energy on the right-hand side is and the geometry of space-time. But just for simplicity, let's take the total energy, gravitational plus kinetic, to be zero. Does it make sense to think that the energy is zero? Yeah, there's a positive term and a negative term. You can make it zero. What does making it zero mean for a projectile when you shoot it up? It means it's at the escape velocity. Okay? It means it's exactly at the escape velocity. If the energy is positive, then it's beyond the escape velocity. If it's negative, it means it falls back down. Okay? So we'll come back to that. Right? Three cases. The energy could be positive, it could be zero, it could be negative. I'm going to take the simplest case, and then we can come back and talk about the other two cases. The simplest case is that the total energy is zero. It corresponds to things being shot out at exactly the escape velocity. Right? It's the simplest cosmology. Yeah.
But capital M varies with time.
Oh, no. No. Capital M does not vary with time. It's all the particles that are in here. But remember that they all move together. So as that sphere expands, the same number of particles, that's an extremely good point, or extremely good question. It was a lousy statement. It was a very good question. The same number of particles is always in that sphere. So it doesn't change with time. But now let's write it in terms of the density of matter in the universe. The density of matter in the universe is the mass per unit volume. That does change with time. As the universe evolves, the material in the universe gets thinner and thinner. This means per real volume, real genuine volume measured in cubic meters. So the amount of mass in a cubic meter, that cubic meter stays fixed. All right, the cubic meter is just a cubic meter. The material moves out of it, and the mass and the density does go down. The total mass stays fixed. The density decreases. The density decreases, the volume increases. All right, so this is the mass per unit volume. What is the total mass inside that shell? The total mass inside that shell is the density. Rho is a standard notation for density. Is density times volume. Volume, what's the volume of a sphere? Anybody know? 4/3 pi r cubed. So 4/3 pi rho r cubed. That's m. Keeping in mind that rho depends on time. We'll discuss later how it depends on time. Okay? But basically it depends on time just because the volume of the sphere increases and the mass doesn't increase. So if the volume increases and the mass doesn't increase, rho depends on time. That's the total mass in there. So now we can write down, let's do this in steps first of all. This is the formula for the mass inside the ball, in the ball. Notice if I have 0 on the right-hand side, and this is one of the reasons that I'm taking the case 0 on the right-hand side, because it makes it a little bit easier, we can divide by the mass of the projectile. So let's do that. Let's just divide it out. Doesn't make any difference. It doesn't matter if that is a galaxy, a star, a pebble. We've just divided out its mass. It's gotten out of the equation. Okay. Setting the difference of two things to 0 is the same thing as setting them equal to each other, so let's just do it this way. And now let's plug in, for the mass, let's plug in what we have here. So I don't think I want to mess up that equation any further. Let's leave it up there and work on it down here. Okay, so let's just substitute now the equation in the box for capital M. That says that 1/2 the square of the velocity, okay, of the outgoing projectile is g over r. And now let's put it in 4 pi over 3 rho r cubed. G is Newton's constant. It came from the right-hand side of the energy equation. The r is also from the energy. And then the rest of this is just the mass inside the shell of radius r. Okay. Now let's use Hubble's law. Hubble's law says that the velocity is equal to the Hubble constant times the distance. Okay. It can also be written in another way, and I'm going to do it this way. I'm going to write the velocity is equal to a dot over a times the distance, because the Hubble constant is just the ratio A dot over A. Okay, let's plug that in and see what we get. I guess I can continue to call it the Hubble constant. We have 1/2 the Hubble constant squared times the distance squared. And the left-hand side is proportional to the distance to that outgoing galaxy squared. Why? Because of Hubble's law. All right. Now, h, of course, depends on time, but we can use it in this equation. And that's equal to g. Well, let's take out the constants first. 4/3 pi, the density of matter, 4/3 pi g, the density of matter, 4/3 pi g, density of matter, r cubed over r. That's r squared. Oh, that's kind of nice. We have r squared on both sides of the equation. That means we can cancel it out. That's kind of interesting, because what it tells us, it had to cancel out. I'll tell you why. Because the Hubble constant, if we have some way of calculating it, which we do now, the Hubble constant can't depend on how far away the galaxy that we're studying is. It's supposed to be the same for all the galaxies. So it better work out that the equations, if they're going to tell us what the Hubble constant is in terms of other things, it had better not depend on how far away the galaxy that we're studying is. And it doesn't. We could have, that's us, we could have used this galaxy, we could have used this galaxy, we could have used this galaxy. They would all give us the same formula for the Hubble constant. And what does it say? It says that the Hubble constant is in some way, not in some way, the square of the Hubble constant, let's write it in the traditional way, the square of the Hubble constant is 8 pi over 3 Newton's constant times the density of matter in the universe, times the density of mass in the universe.
Rho is a function of position.
It's not. On large enough scales, the density of material in the universe is constant. It's a function of time. And so is the Hubble constant. Yeah, we could write it, that's right. We could write this another way. We could write it as A dot over A squared is 8 pi g over 3 times rho of t.
You had to assume that v was the escape velocity.
Or equivalently, that the energy was 0.
Is there evidence that that's true?
Yeah. I'm going to tell you what the evidence is soon. Well, there's one simple piece of evidence. We can measure the Hubble constant, and we can measure the density of matter in the universe. I'm not going to tell you whether they're the same or not. That's because I haven't told you about dark energy yet. But when all forms of mass are accounted for, remember, first of all, you'll hear the term dark energy all the time. Energy and mass are the same thing. E equals mc squared. C is just a conversion factor from energy to mass. So when I speak of mass, I could also be speaking of energy. In units in which the speed of light is 1, rho can be taken to be energy density. Energy density, mass density, same thing. And there are a variety of different kinds of energy in the universe. Different kinds of mass, different kinds of energy. There's the masses of stars. There's intergalactic dust. There's something called dark matter. And on top of everything else, there's vacuum energy. When all of it is added up, the answer is yes, these two equations look like they balance to about 1%. So, we could keep the other term that I threw away, which was just the constant energy here. We could keep it. And I will tell you eventually what it does. What it does. Okay. So yeah, you can first play the game of finding all the energy in the universe, everything we know about, putting it on the right-hand side, measuring Hubble's constant, and after many decades and finding this kind of energy and that kind of energy and so forth, this equation looks good. Okay.
So how much of the
However, it does not mean that the universe is at the escape velocity, because I have made we're going to make some. I'm going to show you some assumptions that came into that. Now, how does rho depend on time? That's the big one. How does rho depend on time? Rho, we take some box in the universe with a certain volume. It's the mass in that box, let's call it m, divided by the volume. Okay? There are various kinds of situations. Let's take the first situation, the simplest situation, that the box is filled with particles. The particles aren't moving very fast. They're more or less at rest. They're what we call galaxies or what else. They're at rest relative to the coordinates x. So we have a given box. It's delta x on this side, delta y on this side, and delta z in the other direction. And we're following the box as it expands. It has a certain number of particles in it. And let's say that number of particles stays fixed. Each particle has a mass, and it's not and they're not moving relative to the coordinates. Then what's the energy in there? The energy is just the total mass, which is the number of particles which stays fixed, divided by the volume. But what is the volume? The volume is the size of the box, delta x times a cubed. All right, so whatever the size, whatever is in that box, the density gets diluted by the fact that a grows with time. This is just the statement that the box gets bigger and bigger. A given amount of mass in a box that gets bigger and bigger, the density will get smaller and smaller. And it will get smaller and smaller according to 1 divided by a cubed. So we can say that the density of mass in the universe is some constant divided by a cubed. Okay. What is the constant here? Well, there's one simple way to specify the constant. The simple way to specify the constant is to say, what is the density of mass today? On the left-hand side, I could put the density of mass today. On the right-hand side, I could put the scale factor today. Now I can multiply it. Let's see, what do we want to do with it? All right, that's a correct equation. Now, how about at any time? Let's write the same equation except at any time. Rho of t is equal to c divided by a cubed of t. And let's divide these two equations, this one by this one. That tells us that rho at any time t divided by rho today, that's this divided by this, is the ratio, the c's cancel out, and it's just the ratio a cubed today divided by a cubed of t. Rho of t divided by rho today is a cubed today divided by a cubed of t. And that's because rho in each case is proportional to 1 over a cubed. Okay, so it's just dividing these two equations. And now we can write that at any time the density of matter, the density rho, is just whatever it is today times the ratio of the scale factor today and the scale factor at an arbitrary time. Okay. The scale factor today is going to drop out of all the equations. But basically the thing that it tells us is that the density of material decreases like 1 over a cubed. We can now try to put that into here. We have on the left-hand side something involving the time derivative of a itself, and this unknown rho of t. But now we know something about rho of t. We know, let's write it out again, a dot divided by a squared is equal 8 pi g over 3. And now rho today, which we measure. Anybody know what the density of material, the density of mass in the universe is roughly?
Seems like you have to guess at how many neutrinos there are. And
Yeah, but that's negligible neutrino density. 1 atom per cubic meter. No. But that's not all of it, because it leaves out the dark matter and the dark energy. And if you include it all, it's about 50 atoms. But it's of that order of magnitude, and it's something that in principle we could measure it directly. In principle, direct measure of all the energy around. So what are we doing? We have rho today. We have a cubed today divided by a cubed of t. Now, 8 pi g 3 rho today and even a cubed today are constants. That is to say, they don't vary with time. Of course, rho varies, but rho today is just rho today. It's just a number that we measure. What about a today? It is just whatever a is today. Okay? So it's just frozen. It doesn't change with time. The only things which change in time are a dot, and a cubed over here. So altogether, we have an equation which looks something like this. A dot over a squared is equal to some big constant. Let's just call that constant c. It contains 8 pi g 3 rho today, a cubed today, all those things which don't change with time, divided by a cubed. This is a differential equation that in principle will tell us how a varies with time. I'm going to solve it for you. Well, let's just solve it. We'll solve it. It's easy to solve. The first thing, let's just multiply on both sides by a squared to get the a squared out of the denominator on both sides. So let's do that. We have a dot squared. Let's put it over here. A dot squared is equal to c. I think it's just divided by a. Right? I've multiplied on both sides by a squared. We can take the square root The square root of a constant is just another constant. And what it says is that the time derivative of a is proportional to 1 over the square root of a. Let's try, rather than to solve it by doing integrals and so forth, let's just try to solve it by saying a is some power of the time. Some power, some coefficient, another constant. Give me another name for a constant. K. K times t to the p. Okay. What is a dot? A dot equals k p t to the p minus 1, right? And on the right-hand side, we have the square root of this constant. And now we have 1 divided by the square root of a, which is a to the minus 1/2. There are two things that I don't know. I don't know the constant k, and I don't know the power t. But now I look at this equation here, and there's only, sorry, this is, did I make a mistake here? Not, sorry, let's do this right. Sorry, mistake. Let's put down, it is a to the minus 1/2, but a to the minus 1/2 is k to the minus 1/2 t to the minus p over 2. A to the 1/2 is k to the 1/2 p to the, t to the p over 2. All right? So I just plugged in for a to the minus 1/2, k to the minus 1/2, and t to the minus p over 2. For this equation to make sense, two things have to match. The powers of t have to match. That would just tell us that the left-hand side and the right-hand side vary the same way with time, and the coefficients have to be the same. That'll be enough to determine both the power and the coefficient. So let's determine the power. The power says that p minus 1 equals minus p over 2. I'm just equating p minus 1 to minus p over 2 to make sure that the left-hand side and the right-hand side vary the same way with time. Okay? So what does that give? That gives p is equal to 1. Let's get all the p's over to the left side. So that's 3p over 2 is equal to 1, or p equals 2/3. All right, what does that tell us? That tells us that the universe expands like p to the 2/3, t to the 2/3. T to the 2/3 is not as fast as just t. T to the 2/3 increases more slowly than t itself. It's bigger than t square root of t. What it is just what it is. A grows like t to the 2/3. And so it just gets bigger and bigger and bigger in this manner here. Okay, now we know what p is. P is 2/3. We can look at the constants, the coefficients. So that says, let's put it over here, kp, and p is 2/3. Two-thirds k is equal to the square root of c, I've forgotten what c is by now, times k to the 1/2. And so now we can divide by k to the 1/2. We have k to the 1/2. And we have k equals c times 9/4. What was c? Anybody remember what c is by this time? Yeah. Okay, let's try to see what it says. Let's come over to here and I don't know what it says. We're going to find out. Let's see what it says. Okay, so we have k equals 9/4 c. K equals 9/4, which is not so interesting, but what is c now? I've forgotten. Can somebody remind me? Where is it? Again, start over. What is it? 8 pi g over 3 rho today a cubed today. Whew, what is this going to say? And now k times t to the 2/3, t to the 2/3 equals a. Something's wrong with this equation. T to the 2/3. I don't know what's wrong with it. There's something wrong with it. No, it looks right. It looks right. But the main thing here is we've determined how the universe expands. It expands with a scale factor that increases as the 2/3 power of time, a to the 2/3. A equals t to the 2/3. With some known coefficient. Did I do something wrong? Was there this? I don't like the look of this equation. We should have the same power of a on both sides of this equation.
I think the power is supposed to be 1/2 instead of 2/3.
Well, you got it wrong.
Okay.
How'd you do that?
I thought I solved it right, but I must have made a mistake.
Well, let's do it a different way. Let's do it a different way. We had that a dot over a was proportional to some constant divided by a, I think. Is that right? Square root of a. Square root of a. So let's multiply by a to the 1/2. Multiplying by a to the 1/2 here would give us a dot. All right, so that would give us. No, let's not do that. A to the 1/2. What is it?
It was c over a cubed.
I've lost track. Here it is. A dot. Yeah. A dot over a squared. A dot over a squared. So we first multiplied by a squared to get rid of the a squares in the denominator. That gave us a dot squared. That's what I meant to write down. Is c over a. Now I think I have it right. All right, and this is dA and dA by dt squared. Let's multiply it by a. And now take the square root of both sides. Square root of both sides gives us square root of a dA dt equals a constant, right? Square root of a constant is just another constant. Now let's multiply by dt. And integrate. What's the integral of constant times dt? Constant times t. C times t. Constant. What's the integral of a to the 1/2? A to the 3/2. So a to the 3/2 is proportional to t, and and a is proportional to t to the 2/3. Okay, so 2/3 is right. So this is an example of how nothing more than Newton's equations is enough to tell you the expansion properties of the universe. And it just continues to expand. It's interesting to ask what happens to the Hubble constant. What will happen to the Hubble constant with time? We know that a is some constant different, all of these constants are different, but we know that it's a constant times t to the 2/3. What about a dot? A dot is 2/3c times t to the 2/3 to the minus 1/3. Just differentiating t to the 2/3, you get t to the minus 1/3, or 2/3 times t to the minus 1/3. Now take a dot over a. That's the Hubble constant. The Hubble constant is a dot over a, so that's 2/3 c t to the minus 1/3 divided by c t to the 2/3. C's cancel, and you find that the Hubble constant is 2/3 over t. That tells us how the Hubble constant will change with time. All right? So this answers the question, at least with the assumptions that we've made, this answers the question of how the Hubble constant varies with time. If this is the way things really work, and we do look back into the past, then we should account for the fact that the Hubble constant increases like 1 over t. All right, so this would give us, we now have a detailed prediction for what we should see very far away. We should see things moving away from us with a Hubble law, but the Hubble law changes with time. So the further away we are, the bigger the Hubble constant should look to us according to this formula. And that's a pretty good representation of what actually happens. To go beyond this, we have to know something about the general theory of relativity. And that's beyond the level of what we're doing. So I'm going to tell you facts. We discussed the fact that there are 3 geometries that can describe homogeneous isotropic universes. We can call them positively curved, zero curved, that's this case that we've been doing, and negatively curved. There are also 3 possible values for the total energy: positive, 0, and negative. These go together. The 3 possible values of the energy, or the 3 possible signs for the energy, plus, 0, and minus, are in 1-to-1 correspondence. And this only follows from Einstein's equations. This you cannot derive just using Newton. Positive total energy, first of all, means that the universe is beyond the escape velocity, and it will continue to escape. It will continue to go out. Positive total energy means negative curvature. So such a cosmology would not only be eternal into the future, but it would also be eternally infinite in space. Okay? Negative curved space goes on and on forever, but it wouldn't be flat space. It would be negatively curved space. All right? 0 total energy, that's the case we did. That corresponds to 0 curvature, flat. And negative energy, that corresponds to positive curved universe, like a sphere. But positive energy, this is negative energy. Negative energy also means that you're below the escape velocity. Negative energy means you're below the escape velocity. The implication of that is that the universe will go out and expand and then turn around and recollapse. All we have to do is focus on that one particle out there that we were studying. The one galaxy that we focused on, all that mass in there. If the velocity is above the escape velocity for all the mass that's in here, concentrated at a point, if we're above the escape velocity, that means the energy is positive, and it means the universe will continue to expand forever. If we're below the escape velocity, and that's the case where the total energy is negative, then every single galaxy will turn around and fall back in. At least according to the assumptions we made. Now, there's a number of things wrong with what we did. The most important is that we have assumed a model for the energy density and the way it varies with time. We said in a given volume there's a fixed amount of mass, and that mass will simply stay the same as the volume increases, and that was the origin of the statement that the density, do we have it here? That the density goes like 1 over a cubed. The volume increases, the amount of mass inside stays the same. Is that necessary? Well, there are lots of examples where that's not true. Let's take the following case. Supposing instead of galaxies or bowling balls or even protons or neutrons, supposing what's in this box is photons. Photons of all different kinds of wavelengths. Okay? Mass is energy. So what we're interested in is the amount of energy in this box as it expands. What's the connection between the energy of a photon and its wavelength, first of all? E equals h nu. So the energy of each individual photon is h times its frequency. We can write that in terms of the wavelength. Frequency over wavelength. Frequency over wavelength. So the bigger the wavelength, the smaller the energy of a photon. Now, what happens to, if we have a box and we expand the box, what happens to a photon of a given wavelength? Well, the answer is it just stretches out to match the box. So the wavelength of the photon will get bigger as the box increases. The number of photons in the box will stay the same. The average number of photons in a box will stay the same. If the box gets bigger, then the wavelength will get bigger and the energy will decrease. So we have a box then, not with a bunch of particles with fixed energy, but a bunch of particles whose individual energies are decreasing.
Why does the wavelength get bigger?
Stretches with the box. It's the same phenomenon that happens if you have a guitar string, and there's a guitar string between two posts. You put your finger down over here so that the effective guitar string is only this long. You pluck it, and then you move your finger. What happens? You hear the tone go from the tone associated with this length of string to a tone associated with this length of string. What happens is that, that the wave you started with just gets stretched out. So you can test this theory if you own a guitar. If you play the guitar, you'll know this very well. So if the container that a bunch of photons are in increases in size, then the energy of each photon goes down. And if the energy of each photon goes down, that means that the energy density in there decreases even faster than it would if each photon stayed with the same amount of energy. If it stayed with the same amount of energy, that's the situation where the density is c over a cubed. What happens with a box of photons is it goes as c over a to the 4th power. It decreases more rapidly as the box. That's easy to derive. You just say that each photon, instead of having a fixed energy, has an energy that goes like 1 over a as the universe expands. And so you get the same formula, except an extra power of a in the denominator. You go right back to over here. And instead of saying that rho goes like 1 over a cubed, you say that rho goes like 1 over 8 to the 4th. And redo the entire analysis, and then you get a different answer. You don't get 8 to the 2/3. You get 8 to the 1/2. In other words, the universe expands a little more slowly. A little more slowly than it would. 8 to the 2/3 expands a little faster than 8 to the 2/3. Is that right? Yeah. Sorry, t to the 2/3. T to the 1/2 is a little slower than t to the... yeah, that's right. Okay. Now, there's a... Okay, so the answer depends on the nature of the energy. Very, very early in the universe was filled with hot photons. Most of the energy was in the form of photons. Notice, if it's true that as you expand the box, the energy of each photon decreases, it's also true that if you squeeze the box, the energy of each photon increases. If you take a box with a bunch of photons, low energy photons, very low energy photons, let's say, and a bunch of protons, then the protons and neutrons and electrons and so forth, atoms, then the atoms will ordinarily be most of the mass in there. But then you start squeezing the box. The atoms, each atom stays the same mass, but each photon, you increase the energy of it. So eventually, when you squeeze it enough, the photons will become the dominant form of energy in the universe. This is going back in time. Squeezing the universe means going back in time. Sometime in the past, when the universe was about 1,000 times smaller in radius than it is now, when the scale factor was about 1,000 times smaller, the dominant form of energy was not particles, ordinary particles, but photons. At that time, the universe was expanding like t to the 1/2, not t to the 3/2. Incidentally, by now, we have good evidence for this. We have good evidence for essentially all of this. So before the time, there's a crossover time when the universe became dominated by ordinary matter, and before that, it was dominated by radiation. Okay, so this is called the radiation-dominated universe. T to the 2/3 is called the matter-dominated universe. Right. There's one other example which is extremely important, and it's the energy of the vacuum. Now, I'm not going to tell you much about the energy of the vacuum. I'm going to tell you only one thing about it. The thing which is true of vacuum energy. And there is vacuum energy in quantum field theory. It's a component of the energy which does not dilute when you expand the universe. Whatever the vacuum energy is, it's a property of empty space, and no matter how big the universe gets, the vacuum energy density stays the same. For our purposes, that defines vacuum energy, a component of the energy that just doesn't go down as the universe expands. Let's just see what it would do. Supposing there was a component of the energy which just refused to decrease. Let's just call it constant. It's the vacuum energy. In fact, it's about 70% of all of the energy in the universe. So it really is the dominant thing today. It doesn't go down. It's also true that as you go backward in time, it doesn't go up. If you take all the other forms of energy and you squeeze it into a smaller volume, the energy goes up. So in the past, the vacuum energy was not so important. In the future, as all the other terms in the energy get smaller and smaller and smaller, 1 over a cubed, 1 over a fourth, the vacuum energy will become the most important component. It's already the most important component by a factor of 2 more. 70% is vacuum energy. Let's solve this equation. What does it say? it says dA by dt, 1 over a, I'm taking the square root of it, is the square root of 8 pi g over 3, that's a constant, times rho to the 1/2. That's also a constant. Everything on the right-hand side is a constant. I'll multiply equation by a. This says that the time derivative of a is proportional to a constant times a. What's the solution of that? Exponential. The time derivative is a constant times the thing itself. Okay? The solution of this is exponential of square root of all this stuff times t. All the stuff being the stuff in here. So this is an exponentially expanding universe. A universe which is dominated by vacuum energy expands exponentially. How long does it take for it to double? Well, it looks like with the present value of the vacuum energy, it takes about 10 billion years for it to double. So it looks like we're heading off into a world where the universe will simply be doubling roughly every 10 or 12 billion years. Why that's true, we don't know. But it's an empirical fact. It appears to be an empirical fact that there's a component of the vacuum energy which is constant, which doesn't dilute as you expand, and which causes the universe to exponentially increase. And in fact, when we look out into the universe, it does appear to be exponentially increasing. If you look far enough away, very, very large distances, it looks like the universe is exponentially expanding. So that's, I've told you a small fraction of everything there is to know about cosmology, but I've told you really the main tools and the main facts about it. Any questions? Yeah.
Thanks. First, the vacuum energy in some sense corresponds to dark energy, but they're not the same thing.
Yeah, same thing.
Same thing.
Same thing, absolutely.
Second thing is, we define the co-moving coordinates. How do the photons know that we've defined the coordinates to be increasing and going to decrease their energy?
Yeah. I think the best way to think about it is in terms of this rubber sheet picture. Space is like a rubber sheet in general relativity. And the photons, of course, don't know that we defined anything at all. Okay? But they can tell that a region of space has doubled in size. They can tell that one wavelength, a region of size one wavelength, in a certain amount of time may have doubled in size or done whatever it does. That's really all they can tell. They can tell the stretching of space.
They know the galaxies are moving apart.
Well, they don't even know anything about the galaxies. They know that space is separating. But yeah, I mean, you can remember that those photons, another way to think about it is through the Doppler shift. Let's see. Where did the photons come from in the universe? They came, let's, okay. Let's draw a picture of the universe from our own perspective. We're sitting at the center, and we're looking out around us, and we see shells of different radius, let's say. There's the solar system is like that. There's the galaxy that surrounds us, which is like that. There's distances out to the Coma supercluster, which is out there. And if we go out far enough, we go to a place called the surface of last scattering. Now, as you look deeper and deeper into the universe, the material was more and more squeezed. And because it was squeezed, it was hotter. So as you look out, you not only see earlier times, but as you look far enough out, the material out here was dense enough and hot enough that it was opaque. It was as opaque as the sun. Somewheres out here, it was as hot as the sun. And you simply can't see through the sun. The sun is opaque. It's opaque because it's full of unmatched electrons and protons, free electrons. It's a plasma. Light can't move through a plasma. Well, far enough into the early universe, the universe was a plasma. But when we look back in time, and eventually we see back to the time when it was a plasma. That's called the surface of last scattering when we look back. So there's some sphere around us that's looks as hot as the sun. But it's also moving away from us with almost the speed of light. Why? Because of Hubble's law. So today, if we were to plug in the numbers, or we were just to look back and use what we know here, we would discover that that surface of last scattering is moving away from us, or was moving away from us. Of course, we're looking back in time, but it's receding away from us with almost the speed of light. That means that a photon that comes from there is Doppler shifted, and it's Doppler shifted a lot. It's Doppler shifted a lot because this surface is moving away very, very rapidly. Okay, now what about, and once you know that it's Doppler shifted, you know something about the wavelengths. The wavelengths of the radiation that are coming from this hot surface are about the same as the wavelengths of the light coming from the sun. They're Doppler shifted, and when they're Doppler shifted, they're elongated, and we see them being roughly 1,000 times longer wavelength than the photons of the sun, and 1,000 times less energetic. Okay? So we see long wavelength photons here because they've been Doppler shifted. Now let's go back into the past and ask what the same picture would have looked like much, much earlier. Much, much earlier, the surface of last scattering would have been closer into us. If we could go back in time and ask our ancient ancestors 4 or 5 billion years ago, what did the universe look like? They would say the same picture, except that they would say the surface of last scattering was closer and moving more slowly. Moving more slowly. So they would see less of a redshift, right. They would see less Doppler shift because they would see the surface of last scattering moving away from them somewhat more slowly. Right? In fact, if you go way, way back, the surface of last scattering was very near and hardly moving at all. Hardly moving at all, and as time went on, it receded and sped up and sped up and sped up. Okay? So the photons, if we went back in time several billion years, the photons that we see coming from the surface of last scattering would have been shorter wavelengths. So as time goes on, the photons that we see that make up the microwave background, for example, as time goes on, the photons that we actually see right here have longer and longer wavelength because they originated from a place which was moving progressively faster and faster away from us. So that's another way to think about it. Both ways are correct. You can either think that the universe was expanding and each wave got stretched out, and so that's why we see longer wavelengths with time, or you can imagine that the same kind of waves were emitted from the surface of last scattering, but by the time they reach us, they've been more redshifted the later we get to look at them. Yeah.
Here's what I don't understand about this. It's the conservation of energy thing. You have a photon of h nu is emitted. Mm-hmm. All right. By the time it arrives with us, it's redshifted a lot, and it has now less energy. Mm-hmm. What has happened to the energy of that little photon?
Okay, so let's go back. The basic equation that we wrote for cosmology was nothing but energy conservation. With this equation, you can't violate energy conservation. But you have to remember there are two kinds of energies. By the time we go through it, this term over here has morphed into A dot over A squared, the expansion of the universe. The other term over here is just the energy density of the universe. This is energy conservation. And it says there's two kinds of energy in the world. One is the energy of expansion. It's a kind of kinetic energy of expansion. And the other is just the usual things that we call energy. Yeah. Neither one by themselves is conserved. They're just not conserved. They're not conserved. I'll explain it in another way in a moment. But they're not conserved by themselves. Only the combination of them is conserved, and that's the equations we used. So in time, as the energy, let's say in photons, goes down, the total energy in photons goes down, it gets transferred into the kinetic energy of expansion. Yes. Yes. Well, you can think of it as a kind of pressure. What happens to energy conservation? Supposing you really did have a box. And let's imagine this is a box with movable walls. The walls can expand. Let's even make it more realistic. It's not a box, it's a cylinder with a piston. Okay? There's the piston. Piston can go in, it can go out. And we have a lot of photons in here. What happens to that box? That box expands because of the pressure of the photons on the piston. Okay? What happens to each photon? Each photon decreases its energy because its wavelength gets longer. Where does that energy go? It goes into the kinetic energy of the piston. Okay. That's where it goes. It goes into the kinetic, or it might go into friction, but let's idealize it. No friction. It goes into the kinetic energy of the piston. That's what's going on here. The energy, the decrease of the energy of the photons is being transferred to kinetic energy of expansion. So it's a very similar thing to this. And energy is funny in the general theory of relativity. It's conserved, but it's also exactly zero. In this case here, we just manifestly made it exactly zero. The rules for energy in the general theory of relativity are peculiar. Either you take into account all the energies that are around, including the energy of expansion, in which case it's conserved but zero, or you forget this expanding energy and just energy isn't conserved. It just isn't conserved in the general theory of relativity.
Generally, any row that you put in there, whatever the time dependence of the row is, it's going to drive the A to have some corresponding time dependence. So this is what you're saying. You're putting a row in there that has some behavior in time.
Yep.
Really.
Yep.
So.
Well, even if rho is constant with time, because the universe, people always ask, where does all the energy come from? If you have vacuum energy and the universe expands, if you have a constant energy density and the universe expands rapidly, it sounds like the energy of the vacuum is increasing. And that component is increasing. Where is it going? It's going into the expansion here. And it drives the expansion even more rapidly than the other forms of energy. So in thinking about energy conservation in general relativity, you must worry about this term. And this term is very important. It's the expansion of the universe. And it simply cancels. Changes in this cancel against changes in that. Yeah.
In the first expression for the metric that we started from,
yeah,
the scale factor, what was the reasoning that the scale factor multiplies the space part but not the time part?
Oh, we could have had it multiply the time part. It would make no difference. Let me show you why. Yeah. That's definition. Okay, let's suppose it also multiplied the time part. So we have a of t times, let's just write simply dt squared minus dx squared, okay? All right, this is a squared. All right. This is just a redefinition of what we call time. Let's invent a new quantity, new time, which is such that dt, a new time, which is equal to a of t dt. We can integrate both sides of this equation, and we can find out what big T is in terms of little t. Then a squared times little dt squared is the same as just big dt squared. So you can always get rid of an a of t squared in front of a dt squared by a change of definition of time. That's done, but that won't get rid of it multiplying the dx squared. So we'll still have minus a of little t, but we can also think of it as in terms of big T dx squared. So the issue of whether a of t multiplies dt squared is a question of definition. Mathematically, there's no difference between the two forms, although you do have to change the definition of time to go back and forth between them. So, yeah.
If the universe was curved, would we expect to see galaxies coming towards us at a high velocity?
That depends on the magnitude of the vacuum energy. Let's suppose there was no vacuum energy. Okay? If the universe were positively curved, the question is analogous to the following question. Supposing we shoot a rocket out with less energy or less velocity than the escape velocity, and we look at it through a telescope. Do we see it moving out or do we see it moving in? Well, I don't know. I mean, it could be moving out or it could be moving in. The one thing we know for sure is if we wait long enough, it'll be coming in. We could have caught it while it was going out. And we catch the universe as it's expanding. There's no doubt of that. The issue is not whether it's expanding now or not, or what we see when we look out. The issue is if we wait long enough into the future, will everything turn around and crash back on top of us? And if there was no vacuum energy, then the answer would be if the universe were positively curved, it would collapse back on itself. The vacuum energy, if it's large enough, will prevent that. And it certainly does look large enough. So it looks like our future, independently of whether we're curved or whether we're positively curved, negatively curved, or flat, it looks like our future is one in which the universe will simply exponentially expand. Now, that's not such a good thing either. If it exponentially, it's not a good future in any case. Well, if it exponentially expands, eventually all the stars will burn out, everything will cool down, everything will dilute, all ordinary forms of energy will exponentially dilute, because if the universe is exponentially expanding, its volume is exponentially expanding, all the energy densities of all the other kinds, other than the vacuum energy density, will also exponentially dilute, and we'll just be in a universe with nothing in it, or with thinner and thinner energy density. So there is no good end to this story.
Also, a great distance away from us, would there be an increased amount of photons? Because in the early universe, it was dominated by photons, and the universe expands. Since the photons move faster than, say, the matter that was in there, would you expect?
As you look back into the past, the ratio of photons to ordinary particles, well, let's see how to say it. I would say more than saying that the number of photons doesn't get larger than the number of, it's already true in our universe that the number of photons is much, much larger than the number of atoms. 10 to the 10th times larger. So we are dominated by photons. I don't mean the photons from light bulbs. I don't mean the photons from the sun. I don't mean the photons from stars. I mean the microwave background from the Big Bang. We are certainly dominated by photons. Now, as you go back in time, the ratio of photons to protons stays about the same. Okay? But the photons get more and more energetic, and the protons don't. So as far as energy goes, as you go back into the past, the energy will be dominated by the photons. The number of photons will stay the same, but their energy will increase as you go back into the past. The number of protons will stay the same, but their energy won't increase, or at least not as fast. Good. Okay. I'm tired. Let's go home. And this is the last class.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.